Welcome to Maths with Bob. Today we're looking at series and sequences. And the first thing I thought I'd do is we'll just try and work out what is the difference between a series and a sequence. Okay, alright, so let's actually have a look. Let's write a list. 2, 4, 6, 8, ... Okay, so this is a list, okay, or a sequence or a progression. Okay, so it's a sequence. Okay, sequence of numbers, it's a list, okay, or sometimes referred to as a progression. Okay, let's write out another set of numbers. Okay, 2 plus 4 plus 6 plus 8 plus ... Now, okay, the ... on the end just means it's an infinite. Now, the first one, 2, 4, 6, 8, comma, ... that's an infinite sequence or infinite progression. The 2 plus 4 plus 6 plus 8 is in fact what's called an infinite series. So this is a series. Okay, so a series is a sum, really. Okay, so when I have plus signs in a list or inside some sort of brackets, I actually form what's called a sum or a series. Now, if I have a geometric progression or geometric sequence, when I add it up, I get a geometric series. If I have an arithmetic progression or arithmetic sequence of numbers, like this one is an arithmetic one, 2, 4, 6, 8 is going up by 2. We say it's a common difference of 2. Okay, then when I add it up, like 2 plus 4 plus 6 plus 8, I get what's called a arithmetic series, and I can use sigma notation and things for the series. Okay, all right. Okay, well, let's actually have a look at the two types of sequences and series we need to look at. We're first of all going to look at sequences. These are arithmetic and geometric, sometimes called APs and GPs. Okay, for the sequences, APs, arithmetic progressions, okay, and GPs for geometric progressions or sequences. Okay. Okay, so let's actually make up some. Okay, so we want a list, arithmetic, so 5, 10, say 15, ... Okay, and let's make up a geometric one. Okay, 5, 10, 20, ... Okay. Now the first question is, how do I tell? Okay, they all have 5 and a 10. Okay, how do I tend to differentiate, if you like, between arithmetic and geometric? Well, the first thing I need to do is test, or apply a test, if you like. Apply a test for arithmetic sequences and apply the test for geometric sequences. And what is this test? Well, okay, the test for APs is in fact that we have a common difference. So the D is always equal to, here, well, it's consistent, I guess you could say. It's the same common difference. Okay, and with geometric ones, okay, we have a test as well, obviously, and we have what's called a common ratio, and that is, in fact, the division of the terms is consistent. Okay, or is it a common multiplier, if you like? So let's just apply this quickly to these two. So we know, okay, which one is, okay, this is called term 1, term 2, term 3. Okay, the ... just means it goes on forever. It's an infinite arithmetic progression or sequence. T1, same sort of thing for geometric ones. T2, term 3. Okay, so we sort of have a subscript there to indicate the position. So T1 is in position 1, T2, position 2, etc. in the sequence. Okay, so let's actually apply this now. Okay, here we go. What is T3? Well, T3 is 15 minus 10. Is that equal to 10 minus 5? Hopefully it is, and it's, as you can see here, it's just 5. Now, T1 sometimes is called A, the first term. Okay, so this is sometimes called A. The first term is 5. Okay. Okay, so let's have a look here. Put in what's T3 is 20. Is 20 on 10 equal to 10 on 5, and hopefully it is. It's actually 2. This is called R. R is called the common ratio, and D is called the common difference. Okay, so let's write that down as well. Okay, so D is the difference. Okay, it's sometimes called a common difference. A is the first term. Now, a is a first term also in a geometric one, okay? So a is, and we have it now called a ratio here, okay? I'll just call it a common ratio. Okay, and r is a common ratio. Maybe we should actually write common. Sometimes it's referred to as a common ratio, and a is again the first term. Okay, this is a sort of a common difference. Okay. Okay, so we now looked at these two. We actually know that the 5, 10, 15 is an arithmetic one, and the 5, 10, 20 is a geometric one because it has a common ratio as opposed to a common difference. Okay, so let's actually look at some general terms and how do we sum these as well. Okay, here we have the arithmetic and geometric ones. I've actually put another term in, term 4, you can see here, which is 20 in the arithmetic case, and it's 40 in the geometric case. Now we're going to look at what's called the general terms, sometimes called the nth term expression, sometimes referred to it as Tn, okay, which means term number n, okay, which is, there's a formula for it, a plus n minus 1d, and for the geometric ones there's a Tn is equal to ar, using a common ratio, n minus 1. Okay, now the first thing is, let's actually do a quick example. How we calculate T5? Now T5 is the first term, which you can all see here, a and a over here, and the first term is both 5 in both cases, okay? So it's going to be 5, now it's times, well, actually it's addition, the addition of so many lots of the common difference, and you can see here it's n minus 1. Now n is actually 5, so you can see here this is n is actually equal to 5, so it's going to be 4 lots of n minus 1 times the common difference. Okay, we worked out the common difference before, but you can just see it goes up by 5. Okay, so if we work this out, we should get that T5 is 5 fours are 25, 25. So in fact, 25 will be the next one over here. So T5 would be 25. Okay, comma, dot, dot, dot. Okay, so let's have a look over here. Let's try and work out T5 in the geometric case. Okay, T5 again is a, we know is the first term, which is 5, and we worked out before that the common ratio was, what do I need to multiply each term by to get to the next one? It's actually, in this case, 2. So it's times by 2, and again to the power, you can see here, 4. Okay, so we know 2 to the 4 is in fact, 16 times 5, so it should actually be 80. Okay, which is just 5 times 16. Okay, so T number 5 should be 80. Okay, so let's have a quick look. If I double 40, I should actually get 80, so that would be in the 5th position, or term called term 5. Obviously it keeps on going, dot, dot, dot. Okay, all right, so let's now look at how to find the sum of these things, and they're called series. Okay. Okay, well, we're now going to look at using the formulas to find the sums of the arithmetic and geometric series. Okay, you can see here T1 up to T5 of each of the arithmetic and geometric series are written there. The dot, dot, dot just means they're an infinite series, basically. That means they go on forever. We can add up how many terms we like. So let's actually just recap. The sum to n terms for an arithmetic series was n on 2, 2a plus n minus 1, n minus 1 lots of the common difference. Okay, so let's write that. Okay, n minus 1 lots of the common difference d. Okay, and we can see here a is 5, the first term, and the common difference is 5 again. Okay, they're going up by 5s. Okay, so let's actually apply this formula. So we want to actually sum 5 terms. Let's just sum 5. We can add up as many as we like, really, but so let's try 5. So 5 on 2, 2 lots of a, 2 5s are 10, plus you can see here n minus 1, n is 5, so it's 4 lots of the common difference 5. And we should see here, what's that? 4 5s are 20, 30, 30 times, okay, so it's 30 times 2.5 at the front there, which is, you can see, 2 30s are 60, and half of 30 is 15, so it's 75. So, in fact, the sum of 5 terms is 75 using the formula. Now, you can actually just do this manually. 25, 20, 15 is 50, 60, and then 10, 70, and then 5 is 75. Okay, so you can just add them up physically or manually if you want. I'm just going to now quickly just use that other formula because we do know term 5, or the last term in this case, is 25. So let's just use the Sn is equal to n on 2. Okay, let's just try that again. Okay, let's just use Sn is equal to n on 2. We'll have a plus L being the last term. Okay, the last term. Okay, L. Okay, so let's try that. Okay, so we want to find sum 5 again. So sum 5 would be 5 on 2 again at the front, because n is 5. A is 5. Now L is actually the last term which we're adding up, and this is term 5, which is 25. So again, you can see here we have like 30 times 2.5, or 2.5 times 30. Okay, times 30. Let's just fix that up a bit. Okay. Two and a half times 30, which is obviously 75. Okay, 75. Okay, boy, the pen's playing up a little bit. Okay, so let's try the geometric ones. Now, you might remember the Sn was equal to what? A r to the n minus 1 on r minus 1. And that was for r being bigger than 1. Basically, the absolute value of r being bigger than 1. Okay. So let's apply this formula. Say S5, okay, is going to be equal to A again, which is 5. The r now is actually 2. So it's 2 to the power of 5 minus 1 all over. Okay. So the pen's playing up a little bit. Okay. 2 minus 1 all over 2 minus 1. And you can just see there's 1 on the bottom. 32 minus 1 is 31, so it's basically 5 times 31. 31. Okay, 31. And you can see that's 155. Okay, so sum of 5 terms is 155. And you can actually do that one manually as well. 80 and 40 and 20 and 10, 5. You can add those up as well. And you should get 155. Yes. Okay. Now, the interesting thing is there a sum to infinity for this particular series? Now, the first thing is, for a sum to infinity or a limiting sum, it needs to converge, but it needs, not only that, it needs to be geometric in nature. So, obviously, arithmetic series don't have what's called limiting sums. Okay, geometric ones do. There are lots of other types of series, but we're just looking at arithmetic and geometric at this moment. And so there's, first up, no limiting sum. Why? Well, hopefully we can see that it's diverging, its sum's getting bigger, but not only that, the test is actually that r is actually has to be less than 1, and obviously in this case it's not less than 1. In fact, r is in fact 2. Okay, we'll look a little bit more at this shortly. Okay, well, we're now going to have a quick look at limiting sums and having a bit of an idea of how we can actually tell whether they're going to exist or not, and whether they are, well, the actual series are going to converge or diverge. Well, if you have a quick look at the middle, well, not quite the middle one there, it's actually this one here. We have, okay, A is 50 and R is actually 2. Okay, so it's actually, each term gets bigger and bigger. This is actually called diverging. And so is a limiting sum existing? No. Is it a geometric? So the first, I guess, thing is it a geometric series? In this case it is. Okay, so it's a geometric series. That's a GS. Okay, so that's good. Okay. Now, is R in the right range? Now, the value, absolute value of R is actually greater than 1. Okay, so therefore, no limiting sum. Okay, let's look at the first one. Okay, we have A. Now, I guess A. Now, is it an arithmetic or geometric? Well, hopefully we can see that we are halving each term. Okay, so we know R is actually equal to a half. So R is in the right range. Okay, it's a geometric series, yes. Okay, good. Okay. R is actually here. The absolute value of R is actually less than 1. Good. Okay, so S infinity does exist. A on 1 minus R. Let's just see what it is. Okay, it would be what? 50 on 1 minus a half. Okay, which would be equal to 100. Okay, so if I add up 50 plus 25 plus 12 and a half plus 6 and a quarter plus, I'm going to approach a value of 100. So I say it converges, the sum converges to 100. Let's have a look at the third one down here. A is 60. Hold on. This is strange. Yes, it actually has a common difference of minus 10. Okay, so this is an AS. Okay, so first up, bang. Okay, no limiting sum. It has to be a geometric series to start with. Okay, let's have a look at the last one down there, 125. Okay, hopefully we can see that that is actually a geometric series. Okay, so this is a GS. Good. Okay, now A is 100. Okay, what's R? Well, it's 25, 100. Okay, hopefully it's consistent. Yes. Okay, a quarter. So we know R is a quarter. Yes, the absolute value of R is less than 1. Fantastic. It does have a limiting sum. S infinity. Let's actually find it. A on 1 minus R. So that's 100 on, okay, what's that? 1 minus 1 quarter. So it's actually 100 on 3 quarters, or if you like, 100 times 4 thirds. Okay, 400 on 3. Okay, so it's, I'll just write that as 400 on 3. Okay, so let's just write that as 400 on 3. So it has a limiting sum, which, okay, of 400 on 3. Okay, I'll just leave it like that. Okay, so the basic idea is, first of all, it has to be a geometric series. The common ratio has to be in the right range, between plus and minus 1, and then we can apply what's called a limiting sum, or the actual series will converge, and we can find what's called a limiting sum. Okay. Well, here we are again with our arithmetic and geometric series. We're now going to apply this to what's called sigma notation. Okay. Well, here we are again with our arithmetic and geometric series, and now we're going to rewrite these sums as in what's called sigma notation. So first of all, we need what's called the nth term. So let's actually work out what the nth term is. Okay, so Tn, as you know, is A plus n minus 1 lots of d here, and here Tn is equal to AR to the n minus 1. Okay, we know A is 5, so it's going to be what, 5 plus n minus 1. We don't know what n is. After the general term, we do know that it's 5. And you can see here it's just 5 plus 5n minus 5, so it's just 5n. So we can rewrite the general term as 5n. So in sigma notation, we use this big Greek letter sigma. Okay, sometimes we put numbers. So let's put 1 to 5 here. So, and just put 5n here. Okay. And sometimes we actually write n equals 1 to 5, but we don't necessarily need to do that. We just automatically know that the variable takes the values 1 to 5 individually, 1, 2, 3, 4, and 5, and the sigma means add them up. So it basically just means, I'll just show you, put in 1, 5, put in 2, 5 2s are 10, put in 3, 5 3s are 15, in 10, 5 4s are 20, and the last one up to 5 5s are 25. Okay, you can see here, which has generated the first 5 terms of that arithmetic series you can see here. Okay, let's have a look at the idea of, for the geometric one. Okay, we know that this would be what, A is 5, so it's going to be now times 2 to the n minus 1. Okay, we don't know what that is, so this is the Tn is just that now. So in sigma notation, this would be written like this, big sigma, okay, going from, say, n equals 1 to 5, okay, the general term is 5, 2 to the n minus 1, so let's write these terms out. You just put in n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and add them up. Okay, the sigma means sum. So let's try and do it. 1, okay, 5 times 2 to the 0 is 5, plus, okay, put in 2, 5 times 2 to the 1, so it's 10, okay, 10. Put in 3. 5 times 4, 20, etc. Okay, put in 4, let's put in 4. 8 5s are 40. Okay, and the last one would be, okay, plus, what's that, 5. So it's going to be 5, 2 to the power 5 minus 1, 2 to the power 4 is 16, 5 16s are 80. Okay, so I can write the sum up to 5 terms with this what's called sigma notation for a particular sequence. Okay, well, that's all there is for today, and well, thank you for watching. Bye for now.